Hi there, Math 30-1. So today we're going to be talking about how we can use a parent function to transform exponential functions. So in a previous video, we kind of talked about what this parent function looks like. So if we direct our attention to these two here, we can quickly review what these parent functions have the general shape of. Okay, because that's what we really care about sometimes, is just understanding what a general shape of a graph looks like to answer a certain question. So here, this is y equals c to the power of x, where c is just some number that's greater than 1. Now remember, they have specific characteristics. One characteristic is that there is a y-intercept here, okay? That y-intercept, or sorry, not y-intercept, that horizontal asymptote. So let's make sure we write that down so I can say the right word, horizontal asymptote. Okay, the horizontal asymptote is at y equals 0. Okay, another really special point here is our y-intercept. Okay, our y-intercept, again, is when our x value here is made as 0. And remember, any number to the power of 0 is 1. So you get this special point at 0 and 1. So we can make a really rough estimate, put it right there. Okay, and remember this c value here is a number greater than 1. So it could be 1.1, it could be 2, 3, it could be 4.5, anything. But all of these equations are going to have the same thing. They're going to have a horizontal asymptote at y equals 0 and a point at 0 and 1. And then depending on the c value, we either will be steeper exponential growth or it'll be more elongated exponential growth. But either way, this is what most, or actually all, parent functions that have this general formula where the c value is greater than 1. Now remember, this is known as an exponential growth equation. Okay, now here we have like an exponential decay. It's the same idea and it has the two same characteristics. Okay, so those characteristics are that we have a horizontal asymptote at y equals 0. So that's a horizontal asymptote here. Now, the main difference here is c is not greater than 0. It's actually between 0 and 1. Okay, so it's any number like 0.75. It could be any number where the numerator is bigger than the denominator. So like 2 over 3, 5 over 8. Okay, any number that looks like that. Now, just recognize it's simply this type of function or this type of graph just flipped. The same idea works, is that we have a x-intercept at 1. Okay, because remember, any number to the power of 0 is 1. So we have 0 and 1 here. So this graph will have our general shape that looks something like this. And again, this is known as a exponential decay graph. But the two main important things is that we have that horizontal asymptote and a point at 0 and 1. We can use these two things to get ideas of what graphs look like. Now, let's remind ourselves down here of our general kind of function notation on how we apply function notation to transforming these parent functions. Now, things we can see here is we have a, okay, let's just remind ourselves, the value a here is a vertical stretch by a factor of a. Okay, and if we were to do mapping notation, we're simply taking all of our y values and multiplying it by a. Our k value here, we're adding it to the function, so that means it's a vertical shift or translation. So vertical shift / translation. Now recognize this is either k units up, and that's when you are dealing with the f of x adding to k, or k units down. And that's when you're taking your function and you're actually applying that transformation downwards. So f of k minus k. So if k is negative, you're going down. If k is positive, you're going up. And then you have these inside. Remember, these are horizontal transformations. Okay, they actually apply to what x is. So in this case, your b value here, your b value is a horizontal stretch. Horizontal stretch. Now recognize this is by a factor of 1 over b, because remember, the x stretches lie, okay? So you actually take all of your values here, your b values, and you'd multiply them by 1 over b, okay? Now, this h value here, this h value is a shift left or right. Remember, this is a horizontal shift. And remember, another word for that is translation, left or right, okay? And those happen in maybe the opposite way that you think. We think negative is left, but remember, when we're talking about x values, they lie. X plus h will go left, x minus h will go right. And then if we apply this, so this would be moving it left here. So minus or plus h, sorry, that would be moving it to the right. And then your y values stay the same. So realistically, that should all be essentially review up to this point. Okay, but it's how do we actually plug that into our equation? Okay, so remember, this is function notation. This is the actual equation. So these are the transformed equation. Now, things to recognize here, okay? Things to recognize. The best part about exponential graphs and this shift up or down, okay? This tells us the new location of the horizontal asymptote. New location of horizontal asymptote. Of course, if parent function is f of x equals c to the power of x, okay? So recognize that. And it makes sense if you think about it, because remember, let's just talk about the the vertical transformations. For vertical transformations, it is a times y plus or minus k, depending on what kind of k value you have, right? Now, if you think about it, for these parent functions, they're both at y equals 0, okay? So what happens when you multiply a number by 0? Nothing happens. So those stretches don't affect this horizontal asymptote when it's at 0. Okay, so if we're talking about this, the x value does not matter in this case, okay? But we are talking about the y value, okay, which is the horizontal asymptote, okay, which is y equals 0. If we plug that in here, again, our x value we're not even talking about x values. We're just talking about where does that horizontal asymptote go, okay? Any number times 0, which what our parent functions have for horizontal asymptotes, plus or minus k. So at the end of the day, your horizontal asymptote is found at where k is. So if you shift 5 units up, that's where your new horizontal asymptote is going to be found. And I'll show you how to use this. Now, let's go on to a quick example here before moving forward. So I'm actually going to focus on B first and then go to A. Because remember, it's always useful to write out your function notation before you actually create the equation. Now let's talk about this. If g of x equals 2 to the power of x, so this is a parent function. It has the general shape of c to the power of x, but in this case, c is 2. If this thing goes a vertical stretch by a factor of 8, horizontal translation 2 units right, and a reflection about the x-axis and a translation 1 unit up, determine the equation of the image of the function. Okay, well, first off, always list all of your transformations. So our transformations is a vertical stretch by a factor of 8. So I'm just going to put vertical stretch factor of 8. Okay, so we multiply all our y values by 8. A horizontal translation 2 units right. Okay, so this is a horizontal translation 2 units right. A reflection about the x-axis. Now, this is something that confuses everyone. Remember, an x-axis reflection means you're changing all of your y coordinates. So this is a y coordinate transformation. And then a translation 1 unit up. So a translation 1 unit up, we can put as a vertical translation 1 unit up. Okay, now that I've written all these out, I can apply this. Now this is where I'm going to describe L of x, which is our new image function, in terms of g of x. So essentially I'm just going to write the function notation. So here, what are we doing to g of x? And in this case, g of x is 2 to the power of x. What are we doing to this thing? Well, we are doing a vertical stretch by a factor of 8. So that means we're going to multiply this by 8. Okay. We are reflecting about the x-axis. And remember, that means we're changing all of our y-coordinate signs. So this is going to be a negative 8. We have a horizontal translation 2 units to the right. And remember, that's applying to our x-coordinates. So this will be minus 2, because remember, x lies. So negative 2 means we're moving to the right. And then a vertical translation 1 unit up. So we're going to add 1 to this. Now, remember, this is not an equation. This is a description of what you're doing to g of x. You have to know how to go from this and apply it into your equation. So remember, g of x equals 2 to the x, and we want to figure out the image function L of x. We just talked about what L of x is in terms of g of x. Now we have to make this into an actual equation. So the first thing I'm going to do is I'm going to apply what's inside of my g of x. So remember, anything we put in here, we have to replace x with. So this time we're saying plug in g of x minus 2. So, sorry everyone. I'm going to plug g of x minus 2 in for x. So this will get replaced where x is. So this will be x minus 2. And I actually should really make this, because we're going to add some things to it here. Now, we have what g of x minus 2 is. It's this equation. Now, what do? Well, we multiply all of g of x minus 2, which in this case is this, by negative 8. So here, this will be negative 8. So we're going to multiply this by negative 8. See how that got placed there. Okay. And then we're going to add 1 to negative g of x minus 2. So this is negative g of x minus 2, and we have to add 1 to it. So we're going to add 1. And remember, this whole thing is representing negative g of x minus 2. So we're going to add 1 to that. And now we've created our equation, because L of x equals this top equation, negative 8, 2 to the power of x minus 2 plus 1. So there's your new equation of L of x. Okay. Now, number C says, using mapping notation to determine where the point P, 3, and 8 that exists on g of x equals 2 to the power of x went after transformations. So essentially, this point exists on g of x, right? Because if we plug in our x value for 3 into g of x, we'll get 2 to the power of 3, and that equals 8. Okay, so this is just a coordinate point. It wants to know, where did this point go? Where is this point on L of x? where is this on L of x? So what I'm going to do here is I'm going to take all of our transformations and plug it into mapping notation. Okay, so here, these are going to represent my points that are on g of x. And these are going to represent my points on L of x. Now, how do we transform g of x to get to L of x? Well, first off, for our horizontal coordinates, our x coordinates, we have to move 2 units to the right. So we are actually going to apply positive 2 to x because we have to move those things to the right. Remember, mapping notation does not lie. Then what happens? Well, then every y value gets multiplied by negative 8. And then we add 1. Because remember, shifts in translations have to happen last. Now, this point was on g of x, 3 and 8. To figure out where it ended up in L of x, we have this tool now. We can do 3 plus 2, negative 8 times 8 plus 1. 3 plus 2 gives me 5. Negative 8 times negative 8 gives me negative 64. Plus 1 gives me negative 63. Okay, and there's where the point P ended up. So this is the image of P 3, 8 on L of x. Okay, so that hopefully was a good review of everything and then how to actually apply these transformations. Okay, let's move. A few examples, we're actually going to graph these functions. Now remember what we talked about at the very beginning of the video. Our parent functions have very special things that we can use to our advantage in order to figure out what these functions look like in terms of their equations. Now, remember, we have a horizontal asymptote at y equals 0. Recall that y equals 0 does not get affected by vertical stretches, so this a value. That being said, this is only going to be affected by our shift, okay, our vertical shift. So let's see how we can use that to our advantage. Now, anytime you want to graph a new function, you have to find some important critical values. You need to find x-intercepts, you need to find y-intercepts, you need to find asymptotes, and you also should probably find just like 1 or 2 simple points that were on your original graph and where did they go. So the point I'm talking about in terms of exponential functions is it's probably a good idea to figure out where that 0 and 1 point went. Okay, remember we talked about those values up here. Those 0, 1 points are those y-intercepts. So where did they go? So you usually want to use mapping notation for that case. Now, something I want to do before we move forward is we're not going to use this graph or equation. What we're going to use is we're going to use this equation. F of x equals negative 3, 2 to the power of x minus 2, and we're going to do minus 6. Or sorry, plus 6. Okay, so let's just note that we need this to be plus 6 here. So we can kind of get rid of this for now. And we've really only changed one thing. It was plus 6 now. Now, we need to determine the graph of this function. So the first thing you want to do is, well, ask yourself, what does this parent function look like? Well, we can think about the parent function. And in this case, c equals 2. Because remember, all parent functions for exponents is y equals c to the x. But in this case, c equals 2. So our parent function is 2 to the x. So that's a pretty easy one to imagine. Okay, so if we draw a really rough looking graph here, we know that it has a y-intercept at 1. So this is 1 here. We also know that there's a horizontal asymptote at y equals 0. And then for something like 2 to the power of x, there's some easy points here. So like when x is 1, you get y at 2. When x is 2, you get y at 4. Okay, so some easy points to think about, right? So 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, so on and so forth. So these are all coordinate points on our parent function here. Okay, so 0, 1, 1, 2, 2, 4. Now, recall, we can find our horizontal asymptotes very easily, okay? We know that this guy is not affected by vertical stretches. So not affected by vertical stretches. Because remember, if we think about it, right now this has a vertical stretch of 3. If we multiply 0 by 3, nothing's going to happen. And then we're going to add 6 to it. So our new horizontal asymptote is really easy to find. It's at positive 6. Okay. And I'll maybe use a highlighter for this. Okay, so we have a horizontal asymptote at y equals 6. So this was pretty easy to find. So y equals 6 is the new horizontal asymptote. Okay, and that's because of our value here, positive 6. Now, something else we can think about and just keep in the back of our mind is this. That is a reflection about the x-axis. So what is it doing? It's changing all of your y coordinates. So here, if we go back to our parent function, that negative value is going to flip this down here. Okay, it's going to flip it, and then we're going to move 6 units up. So we should know that the general shape of this graph is going to look something like this. Okay, so we can keep that in the back of our mind. So that means when we find our y-intercept, which is what we're about to do here, it will be below 6, and our x-intercept has to be greater than 0. Okay, so let's find those. So let's find the y-intercept. So that is when x equals 0. So your first step here is, well, let's plug in 0 for x. So f at 0 equals negative 3, 2 to the power of 0 minus 2 plus 6. This will be negative 3, 2 to the power of negative 2 plus 6. Now this is something we'll learn, but this is a very easy exponent law that we can use. So note, there's an exponent law that we're going to use, and that exponent law is any number to the power of a negative exponent, you can flip it and take the reciprocal, and that will make the positive exponent. So here, we can take 2 to the negative 2 and make it 1 over negative 2. So this will become 1 over 2 to the power of 2. And recognize, since we've taken the reciprocal, we can now happily make our exponent positive. Add 6. 2 squared is 4, so this will be negative 3 over times 1 over 4 plus 6. We can apply this, so negative 3 times 1 is negative 3 over 4 plus 6. And then from here, what are we doing? We're doing, we need to get common denominators. So we're going to multiply 6 by 4, because we can imagine this to be over 1. So times 4 and times 4. And that will give me negative 3 over 4 plus 24 over 4. Negative 3 plus 24 gives me negative 21 over 4. Okay, so we now have a value here for our y-intercept. So our y-intercept looks like it's negative 21 and 4. Okay, and let's just think about that. That doesn't make sense. I messed that up. Negative 3 plus 24 gives me positive 21. Okay, and why did I know to stop there? So sometimes it's good to see your instructor kind of make maybe a little flub. I knew that was wrong because we talked about how the graph is going to look like this. I knew that y-intercept had to be somewhere around here. So 21 over 4 definitely makes more sense. Let's just maybe get a decimal for that number, just to know maybe what it looks like a little bit better. So let's get out of here. So 21 divided by 4, that gives me 5.25. So that makes a lot more sense. So that means your y-intercept when x is 0 is 5.25. So we're around, if we do 1, 2, 3, 4, 5. We're around right here, okay, which makes a lot of sense. Now, we found one critical value. Actually, we found two already. We know an asymptote, we know our y-intercept. Let's find our x-intercept. So our x-intercept, and that's when your y equals 0 or your whole function equals 0. That's another way to put it. So here our function equals this. So let's make this 0 and solve for x. So here will be -3, or 0 equals -3 times 2x minus 2 plus 6. And now we got to solve for our x value. So I'm going to subtract 6 from both sides. I am then going to divide my -3 first, because remember, we're doing bed mass backwards. So to solve for x, you need to get the things furthest away from it, and we're going to divide by -3 here. That will give me +2 equals 2 to the power of x minus 2. Now here, this is something we'll learn, and maybe you've already learned, but now we have a common base. Remember, this is 2 to the power of 1. When you have a common base equaling each other, you're essentially figuring out when do these exponents equal each other. So here, we can take these, since they have common bases of 2, and we can ask ourselves, when does 1 equal x minus 2? So I'm going to take 1 and make it x minus 2. And then I can add 2 here, add 2, and that gives me 3 equaling x. So it looks like we have a x-intercept at 3 and 0, right? This is our x-intercept. So 3 and 0, so this will be 1, 2, 3 is roughly right here. Now, again, something good sometimes to find is just like maybe find one other point. But at the end of the day, we actually have a really good understanding of what this graph's going to look like. It's going to look something like this. And you can see all the things that happen to this function, right? Our parent function, y equals 2 to the power of x, was an exponential increasing function. We applied a reflection, okay? So this thing ended up going downwards, which looks like this. And then we had to move 6 units up. So our horizontal asymptote used to be here at y equals 0, but then it was moved 6 units up, okay? And we can see that it's been stretched out a little bit, which makes sense because we're going through a vertical stretch of by a factor of 3, okay? So let's see if we can find maybe where one of these points went. Just like I said, maybe find one extra point. Again, it's not super needed, but it is good to have some clarification here. So let's see where just 0 and 1 went, because that's an easy point to figure out. So where did 0 and 1 go? Okay, so I'm going to use mapping notation. So these x and y values are going to be the ones that are on 2 to the power of x. And then over here, I'm going to apply these transformations. So what did we do? We went 2 units to the right. So with my x values, I'm going to add 2. And then we also vertically stretched our y coordinates by a factor of 3 and reflected it. So this will be -3 times y, and then we moved 6 units up. So I'm going to add 6. And this is on our new function. Okay, this is on f of x, which in this case was -3, 2 to the power of x minus 2 plus 6. So here, let's see where that 0 and 1 went. So 0 and 1, 0 plus 2, -3 times 1 plus 6. And that equals 2 and, what does that give me? -3 plus 6 gives me 3. So 2 and 3, and let's see if that makes sense. That actually lines up almost perfectly on our graph. 2 and 3, look at that. So we were able to get a really good estimate of what this graph looks like, okay? And again, we could have, now you understand, if we plug in 2 here, that's gonna give us 3, which we can kind of show here. So f at 2 equals negative 3 times 2 to the power of 2 minus 2 plus 6. And let's just figure all this out. So this is 2 minus 2, which is 0. So this will be negative 3 times 2 to the power of 0 plus 6. Recall, any number to the power of 0 is positive 1. So this equals 1. So this will be negative 3 times 1 plus 6, which is going to give me negative 3 plus 6 being positive 3. So we've just proven that simply this point is in fact on our graph here. So now we have a really good understanding of what this graph looks like. Okay, so thanks for watching, and we're actually going to move on to the next example. I thought the video was over, but we still have 2 more examples here. Okay, so let's talk about example 3 here. So the following function, y equals negative 1 over 2x, which is in a parent form, right? This is in the form of c to the power of x, where c equals 1 over 2. Now we already know what this graph roughly looks like. C is between 0 and 1, so this is going to be an exponential decay. But again, it has a horizontal asymptote at y equals 0, and it has a point, a y-intercept at 1. Okay, so pretty much the same thing, but we already have a really good understanding of what 1 over 2x looks like. Okay, this thing's translated 12 units left, 4 units down. It is horizontally stretched by a factor of b. The image function goes through the point negative 4 and 12. Determine the equation of the image function. Okay, so we got lots going on here. Now, first off, let's call f of x negative 1 over 2x. Okay, so let's just say that right off the dot. Let's say our new function is named g of x. Let's make a function notation of g of x in terms of f of x. So what are we doing to f of x to get to our image function? Well, we're translating at 12 units left and going 4 units down, and we're having a horizontal stretch by a factor of b. So in function notation, what we're doing to f is we're having that horizontal stretch by a factor of b. So in this case, that's actually 1 over b, okay? And then we're going 12 units left. So that's x plus 12. And then we are going 4 units down. So let's see that here. So we have our shift 12 units left, which is what we set up here. We have our horizontal stretch by a factor of b. So this is our horizontal stretch by a factor of b. And then here we have our 4 units down shift. And that's a vertical shift. So again, is this the equation? Absolutely not. This is just a function notation, but it is really useful because now we can apply these to f, which in this case is 1 over 2. So again, let's do that. So in this case, we have f 1 over b x plus 12. Well, how do we apply that to our actual equation? Well, remember, we have just taken and replaced x with b 1 over b times x plus 12. So plug this in for x. So this will be 1 over 2 to the power of 1 over b x plus 12. So look at that. And then again, we can't forget this vertical shift. So we're subtracting this whole thing by 4, so we got to subtract this whole thing by 4. And now we have a rough idea of what this equation looks like. So g of x, which our new equation is 1 over 2 to the power of 1 over b x plus 12 minus 4. Now, we need to solve for what 1 over b is. Okay, so we got to find what b is. How do we find b? Well, we know g of x goes through negative 4 and 12. It told us that in the question. It says the image function goes through the point negative 4 and 12. Okay, so that means when, remember this is x and y, aka this is x and g of x in this case. Remember, g of x and y are replaceable. So if I make g of x equal 12 and x equal negative 4, I can then solve for 1 over b. So let's do that. So when g of x is 12, we have negative 1 over 2 to the power of 1 over b. Our x value is negative 4 plus 12 minus 4. And now we can start solving for this b variable. So the first thing I'm going to do is I'm going to add 4 to both sides. So this will be add 4, and that gives me 16 equals 1 over 2 to the power of 1 over b times negative 4 plus 12. And then here, this is using a common base. Okay, so I know that 16 can be represented by 2 to the power of 4. I also know 1 over 2 can be represented as 2 to the power of negative 2. Okay, so there's videos on this in your slideshow. Okay, so make sure you definitely are understanding your exponent laws, or else this can be very hard. So I can replace 16 with 2 to the power of 4. I can also replace 1 over 2 with that shouldn't be to the power of negative 2, that actually should just be to the power of negative 1. Okay, so here I can replace 1 over 2 with just 2 to the power of negative 1. So this will be 2 to the power of negative 1 times 1 over, to the power of 1 over b times negative 4 plus 12. And then from there, we have 2 to the power of 4 equaling. Now, let's simplify this. I probably should have simplified negative 4 plus 12 a long time ago. So this is 2 to the power of negative 1 to the power of 1 over b times negative 4 plus 12 gives me 8. And then here, we have to apply another exponent law. Okay, your exponent laws in this case are let's think about this. Our exponent laws where we have m to the power of n to the power of a. Well, this where we just multiply our exponents. Okay, so I'm going to multiply negative 1 times 8 times 1 over b. So that will give me 2 to the power of negative 8 over b. Okay, so I just multiplied all of these exponents. Now, we are almost done, but recognize we have similar bases here. So since we have similar bases, we can just equate their exponents. So this will be 4 equals negative 8 over b. And now I can solve for b here. So to solve for b, I multiply both sides by b over 1 to get b on top. So I get b times 4 equals negative 8. And then I'm going to divide 4 from both sides. So that's going to give me b to the negative 2, or times negative 2. And I went all the way into my graph. Okay, so we're going to have to figure that out. But here, recognize we've solved for b officially. So we know what this equation is. So to finish off this question, g of x equals 1 over 2 to the power of 1 over negative 2 times x plus 2, or 12, x plus 12, and then minus 4. So there you go. It looks like we vertically stretched this by a factor of 2, and we also reflected it. Okay, so there is my final answer there. Now, how can we determine the image of this function? So g of x here equals 1 over 2 to the power of negative 1 over 2, x plus 12 minus 4. Okay, Now I'm actually going to make my life a lot easier here. And this is kind of a thing I suggest you guys doing. If you ever have a horizontal stretch, okay, or not a horizontal stretch, but if you ever have a horizontal reflection, so aka reflection in the y-axis, why don't you just apply that here and take the reciprocal? So notice here, g of x can also be represented. I'm going to apply just the negative value to my 1 and 2. So I'm actually going to flip this and take the reciprocal to make this positive. So this will be 2 to the power of 1 over 2 x plus 12. And that's going to make my life quite a bit more simple, okay? Because now my parent function is y equals 2 to the power of x, okay? Which is a lot easier to deal with than 1 over 2 to the power of x. So remember, this all has those same characteristics, okay? So this is an exponential growth because c equals 2. This is at 1, and you have y equals 0. To graph this thing, we already know that our new horizontal asymptote is at -4. So here, we have a horizontal asymptote at -4. We did not reflect anything here. There's no negatives in front of this 2, and there's no negatives in the exponent here. So we can happily deal with that. Now, let's figure out those key points. So where did our y-intercept go? aka when our x equals 0. Okay, so let's just plug in x for 0. And this will be 2 to the power of -1 over 2 times 0 plus 12 minus 4. And that will give me 0 plus 12 is 12. So this will be 1 over 2 times 12 minus 4. And that will give me 12 times 1 over 2 is 6. So this is 2 to the power of 6 minus 4. Now what is 2 to the power of 6? Well, I know 2 to the power of 4 is 16. That makes 2 to the power of 5 to be 32. So that makes 2 to the power of 6, 64. Okay, so this is 64 minus 4, which gives me 60. So we are way up here at 60 for our y-intercept. Okay, now what does that mean? That means my x-intercept has to be here, because remember, we didn't reflect this. So it looks like we're going upwards like this. Okay, so let's determine that. So let's determine where the x-intercept went. So again, that is when your y equals 0 or your entire function equals 0. Means the same thing. So in this case, 0 equals 2 to the power of 1 over 2, x plus 12 minus 4. And then from there, we're solving for x. So add 4 to both sides, and we'll get 4 equals 2 to the power of 1 over 2, x plus 12. And remember, I can represent this guy as 2 squared. So I can get similar bases. And again, if you have not watched that video, you definitely need to go watch it. Because now we have similar bases, so you can solve for these exponents. So I'm going to equate the exponents to each other. Okay, what I'm going to do here is I'm going to get rid of this 1 over 2 by multiplying both sides by 2. This cancels that out, and we get 4 equaling x plus 12, and I'm going to subtract 12 by both sides. So that's going to give me -8 equaling x. So there is your x-intercept. It's at -8 and 0, which should be expected, remember? If this is our y-intercept, we know that our graph has to go something like this. So our x-intercept is at roughly -8 here. So if we draw this graph really roughly, it's going to look something like this. And that's obviously not to scale, okay? But it's going to look something like that. And we can tell it's been stretched, right? We have stretched this thing by quite a bit. But there is our rough graph. And remember, the biggest thing is we found this guy really easily because it's just our vertical shift due to our parent function. And we also know the domain and range of this thing. Okay, so the domain has not changed. X is still any number, right? This goes on forever and ever, left or right. But here, at our horizontal asymptote, that has changed our range. So our y value has to be greater than -4. Remember, it can never equal it because it's just approaching -4 forever and ever and ever and ever. So there is your domain and range. Okay. So now we're going to look at example 4. So example 4, it tells that g of x equals 3 to the power of x, and that the function f of x is a transformation on g of x. Okay, so these are all the transformations. So the first thing I'm going to do before I even start here is I'm going to actually do b. I'm going to describe the transformations applied to g of x, because it's always good to do that right off the dot. Understand what transformations are actually applying. Okay, now some things to remember. Shifts happen last. Okay, so when we go through this, I'm going to talk about the shifts or the translations last, because that's the last step you have to do. Another thing to remember is I'm already looking here and I have an issue. X does not have a +1 coefficient. So I'm going to rewrite this by factoring out this -1/4. So in order to do that, I will leave 9 and it'll be g, and I'm going to factor out that -1/4. So x will have a +1 in front of it, and then you're going to do -1 dividing -1/4, and that's going to leave you with +4. Subtract 1. Okay, so now we have successfully taken out this -1/4, and we can read our shift properly. So what are the things that are happening here? Remember, shifts are going to be talked about last. So let's first focus on this reflection. There's a reflection here, and that reflection is in the y-axis. Okay, so that comes from your negative value there. We then have a vertical stretch. So this is a vertical stretch by a factor of 9. We then have a horizontal stretch, and remember, it is opposite to what you think with x coordinates. So this is actually by a factor of 4. So this is a horizontal stretch by factor of 4. So we take all of our x components and multiply them by 4. Now we can focus on our shifts. So this is a shift 4 unit left because x lies. Shift 4 units left. And then a shift 1 unit down. So now we have successfully wrote out all of our described transformations. Now, again, is this an equation? Absolutely not. This is a function. This is just saying whatever function f of x is, it equals g and all of these things applied to g. In this question, we're given what g is. So in our question, g of x equals 3 to the power of x. Now we actually have to find the equation of f of x. Remember, f of x is technically whatever function this is. Okay, so let's apply these transformations, and how do we go from function notation into the actual equation? Well, first of all, f of x equals g -4 x plus 4. So first I'm going to focus on everything that's happening to the horizontals. So remember, anything inside of g we plug in for x. So we're going to replace x with this, so that means we're going to put it here. So we'll get 3 to the power of -1/4 x plus 4. Then we have to multiply this by 9. And remember, this whole thing is represented by this expression. So I'm going to multiply 9 by this whole thing, aka I'm going to multiply it by this. So this will be 9 times 3 to the power of -4 x plus 4. And then lastly, we have to subtract 1. So I'm going to subtract 1, and I am subtracting this whole thing, which is being represented by this, by 1. So subtract 1. So there is our equation of f of x. 9 times 3 to the power of negative 1 over 4, x plus 4, subtracting 1. Now we have an equation. Let's sketch the graph of this equation. Now remember, anything that looks like this, try and imagine what the parent function looks like. So the parent function, well, it tells us actually what the parent function is. It's 3 to the power of x. Is y equals 3 to the power of x. What does 3 to the power of x look like? Well, 3 to the power of x is simply an exponential function with a y-intercept at 1 and a horizontal asymptote at y equals 0. Okay, now we can get a really rough idea of what this equation looks like. Because the first thing we have to notice is that we're reflecting about the y-axis. So as soon as we reflect about the y-axis, we get a graph that's going to look like this. Okay, so recognize we reflected about the y-axis here. Okay, and we end up getting a graph that looks like this. Now remember, something also useful to know about these parent functions is y equals 0 is not affected by this vertical this vertical stretch, because 0 times 9 is 0, and then we subtract 1. So we will end up getting a horizontal asymptote at y equals negative 1. So that's what our graph's roughly going to look like. So let's draw that here. We have a horizontal asymptote at y equals negative 1 because of that shift. We know our graph is going to look something like this. Okay, it's going to be an exponential decay function because we've reflected it in the y-axis. So that means we're going to have a y-intercept somewhere around here and an x-intercept somewhere around here. Okay, so let's maybe find where those are. Okay, and it might not be here. I'm going to guess that it might be here, but all I know is it's going to be above this horizontal asymptote. This x-intercept could be anywhere here, really. So let's just figure out what this looks like. So let's find the y-intercept. So AK when x equals 0. So let's plug in 0 for x. So I will get 9 times 3 to the power of negative 1 over 4, 0 plus 4, minus 1. So you can see here we've taken our x value and we've plugged in 0 for it. And let's solve this. So this will be 9 times 3 to the power of, well, this will be negative 1 over 4. 0 plus 4 is 4, minus 1. We'll get 9 times 3. 4 times negative 1 over 4 is simply negative 1, and that's subtracting 1. Okay. And now we can bring this up here. And what I'm going to do here is this has a negative exponent, so I'm going to take the inverse and make that exponent positive. So this will be 9 dividing 3 to the power of positive 1, subtract 1. So this is some exponent laws I just used. Okay. 9 divided by 3 gives me 3, subtracting 1, which will equal 2. Okay, so there's my y-intercept. I have 0 and 2. So it looks like my y-intercept actually is above the x-axis, which is okay, at positive 2 here. Okay. Now, let's talk about where some other things go. Okay. So where does my x-intercept exist? Well, I know my x-intercept is going to have to be somewhere around here, because I already know that my graph is going to have a general shape that looks like this. Okay, so that's just something to be aware of. So let's find my x-intercept, and that's when y equals 0, or in this case, when f of x equals 0. So I'm going to take my equation and plug 0 in here and solve for x. So this will be 0 equals 9 times 3 to the power of negative 1 over 4, x plus 4 minus 1. Okay, I'm going to add 1 to both sides, and this will give me 1 equaling 9 times 3 to the power of negative 1 over 4, x plus 4. I'm going to divide 9 from both sides, so I get 1 over 9 equaling 3 to the power of negative 1 over 4, x plus 4. Now, we have to use common bases. Recognize 1 over 9 equals 3 to the power of negative 2. Okay, so there's some exponent laws going on here. So I'm going to replace 1 over 9 with 3 to the power of negative 1 over 2. Now, we can see we have common bases, so I can equate their exponents and solve for x. So I'm going to take their exponents and equal them to each other and solve for x. So what I'm going to do is multiply both sides by by positive negative 4. So negative 4 times negative 1 over 4, well, that gives me 1, so that cancels all this out. Negative 4 times negative 2 gives me positive 8. And then I'm going to subtract 4 from both sides. So subtract 4, and that gives me 4 equaling x. So there is my x-intercept, and that makes sense because here is 4 and 0. Okay, so there's my general equation of this, my general looking graph for this kind of harder looking equation. Remember, we used our parent function. We were easily able to find where our horizontal asymptote is. We had a general idea of maybe where our x and y intercepts could be, and then we solved for those things.